Hi, welcome. I'm Jason Burns from Nutanix. I'm here on behalf of the solutions team, and I want to talk to you today about running unified communications on top of Nutanix. So before we get started, let's talk a little bit about some of the acronyms that we see around unified communications that confuse people. I just want to make sure we're all on the same page. So first, when I talk about unified communications, or UC, I'm talking about a vendor-independent term for my servers and my clients. So UC could be any vendor. It could be Avaya, Cisco, Microsoft, any vendor who makes a platform for communication. UCS, on the other hand, is going to be vendor-specific. That's Cisco's entry for data center and compute. UCM is Cisco's main call control application, so that's their communications manager. Now, confusingly enough, Avaya also has a product called CM, not with a U, just CM for communication manager, and that's their call control virtual machine. So again, UC, unified communications as a whole. UCS, a very specific line of products from Cisco. UCM, a call control virtual machine from Cisco, and CM, a call control virtual machine from Avaya. So why is unified communications important to us? Why would it be a workload that we want to run on top of Nutanix? So to illustrate that, I wanted to tell a story about UC. So let's imagine that we're away from our desk and we miss a call. So I'm out to lunch, I'm running an errand, and I come back, I see that I have a call. And the cool thing about unified communications is I glance at a single application and I see that I have a missed call, and I also have a voicemail. The light is lit on my phone, the light is lit on my desktop client. I can see exactly who it's from, and I can see that, wow, it's 1 minute and 32 seconds in length. It's from someone on the reliability team who has a question for me, and I don't want to answer. I don't want to listen to a 1 minute and 32 second voicemail, so I right click on that voicemail and I start an instant message with that user. So I start a chat right from the voicemail and I say, hey, what's going on? I see this long message, and we chat for a little bit and we say, well, you know, chat isn't working, maybe we can escalate to a video call because we've got to talk about this important issue, and it might be better just to do it face to face. Just another click away is a video escalation. We talk for a little while and then we say, well, now that we've talked, there's this one screen I want to show you so I can show you my results or show you the section I'm concerned with. Again, just another single click, and now we're sharing screens from our video call. We determine that we have some question that we can't answer in our lab system, and we actually want to take a look at the customer system. This is easy to do right from that same interface. We just click and fire up a WebEx session and invite the customer for it, or an Avaya Scopia session, whatever the unified communications screen sharing program is that you've decided to use. So during all of this, we've had a seamless operation from a missed call all the way to a call with a customer. We've been in one single application on our desktop the whole time. We haven't had to click around to other apps. And it's been click, click, click to get from where I started to where I finished with my customer. From the client perspective, this looks like just one single application that can do all of these great things. Now, unified communications on the back end is really a bunch of servers in the infrastructure that made this all possible. So when I talk about unified communications, the benefit is that seamless client integration. And the part that we need to be concerned about for running it on Nutanix is all of that infrastructure backend. So Microsoft has products to provide this integration in the form of Microsoft Lync and Exchange. There's also a Lync phone that you can see down here as well that'll speak SIP and make phone calls. Cisco has their products in the form of Cisco Jabber and all the other infrastructure on the back end that supports it. And Avaya also has their 1X communicator that does their integrated communications. So when you look at all these apps, you'll see something in common. I have some way to have a contact list. I have some way to see my calls. I have some way to easily chat with people, call people, and look at my voicemails. Some of the advanced features you're going to get are going to be the screen sharing as well, and they might choose to do that in different ways for these applications. So let's get started right into what happens in the infrastructure. When I talk about call control, what I mean is the basis of routing voice and video calls. So I have one phone on the left here, and then another phone, one PC with a soft phone on the left, and then a hard phone on the right. Let's say that they want to make a call to each other. They're going to send a SIP signaling message, a lightweight SIP signaling message, much like HTTP, and say, hey, I'm over here, I want to call some other number. The call control says, alright, I see the request, I'm looking up where this guy is for you, so it's going to do a dip into its call routing database, usually an in-memory database, and figure out where the phone is and tell the phone, hey, you've got an incoming call. So the job of call control is to manage the lifetime of that call, and the key things are to set up this RTP stream. This is a real-time streaming protocol, and what it needs to do that is it needs to find the IP address of that destination endpoint and be the man in the middle for the negotiation. So the PC on the left has an IP. It needs to tell call control that. Call control says, hey, this guy wants to talk to you, here's his info, what's your info? And the phone relays that back, and call control manages that negotiation. When the call terminates, call control is in there as well, managing the teardown or maybe even escalation. So let's say we're in a voice call and we want to escalate to a video call. Call control would pass that along. We see that we've got call control splitting up the communication at a multi-tiered approach. So we have a local call control, then a session control, maybe that sits in a data center somewhere, and then another local call control. This can happen because we want to have our call control somewhat local to us. So maybe we have an East Coast call control and a West Coast call control with a session control somewhere in the middle of the country. And let's say the call control on the West Coast manages all the West Coast offices, the call control on the East Coast manages all the East Coast offices. The session control is the place where we can centralize that dial plan and be the border point in between. So again, SIP, lightweight messages. RTP is the direct audio stream. That direct audio stream is going to be routed directly between the endpoints, and it's going to be about 50 packets per second of voice or video stream directly between the endpoints. Again, we've got a legend here, so our SIP we can see is our dotted blue lines. Our RTP voice or video is our yellow line. The next thing I want to talk about is our PSTN access. So this gets us external access to anyone we want to call in the world. So if we want to call the pizza delivery guy, we want to call our mom, we're doing this through a PSTN gateway. The more typical example, I'd say, is customers here. So if you want to call your customers, they're typically going to be reached through a PSTN gateway. The job of the PSTN gateway is to get you access to a provider like AT&T or Verizon, so your calls can be routed on the public switch telephone network. Now again, that's going to be managed and communicated with via the SIP protocol here, and if this IP endpoint down at the bottom wants to make a call, the PSTN gateway's job is to take this IP RTP stream, translate it to whatever the digital PRI signaling or even analog signaling if it's a really old phone line. The PSTN gateway's job is to translate from the IP leg to whatever the PSTN signaling leg is. This PSTN gateway is typically a physical piece of hardware because it has those analog and digital conversion requirements. Now, AT&T, Verizon, other providers have the ability to also do a SIP termination instead of an analog termination, and the PSTN gateway still serves a function in that case. The PSTN gateway in that instance becomes the address hiding portion. It becomes your border element between all of your internal structure and your internal IP addresses, which you want to hide from the world, and the external world. So the external world would reach you via SIP through a PSTN gateway. In that case, we have the option to actually do a virtual PSTN gateway or a physical PSTN gateway. I've just drawn it as a physical gateway here because it's the most common right now. So the next portion that we have is our voice messaging platform. When we have a call come in to a phone, let's say that that's not answered. It has to go somewhere, so the voice messaging platform terminates that RTP audio stream, saves the voice messages to disk, and allows them to be played back at a later point in time. So terminates an RTP stream, and then my PC or phone can call into the voice messaging system, play that message back. Typically that's an RTP stream, but we also have the ability to set up an email client so that it can do an IMAP connection and play voice messages off the server's disk via IMAP mail clients. There's also some other integrations we don't have shown here, which would allow the voice message server to send SMTP mail or even Exchange WebDAV communication directly to an email server. So it would show up in your email inbox. And that's the point where we call this unified messaging, where it's one single client that you have, and it shows you all of your messages that are for either voice or email. And again, this is reached usually via a SIP call control to alert it that there's an incoming call and to manage the setup of the RTP stream that's about to be terminated on that device. The next portion that we have is IM in Presence, or instant messaging in Presence. The main goal of this service is to allow chat communications between endpoints. So it uses the standard XMPP or Jabber protocol to perform that operation. So it integrates via SIP to the call control to do the other half of its name. So the first half is chat, second half is going to be presence. So it integrates with call control for presence. So let's say I'm a PC over on the right hand side here. I have my presence client running, and I'm interested in the state of the user sitting over here doing call control. So I want to know when that user's at their phone. I want to know when they're on a call, and maybe I want to know when they're off a call, because I can see, oh, well, he just hung up his phone. That means maybe I can give him a call now, or maybe I can send him a message now. So the SIP protocol is used between the presence server and the call control servers to subscribe to the presence status of other endpoints in the network. Now, not shown here is also an integration that we can do with email or a calendaring system, so we could see the busy and away status based on what appointments you have. The next server that we have is our conferencing server. So this is usually a pretty beefy server. It used to all be done in hardware, but we're moving more and more to doing things in CPU. The goal of the conferencing server is to take all of the different RTP streams that are coming in at 50 packets per second, mix them, and then spit them out into one unified stream. So if these three endpoints here are in a single conference call, all talking to each other, whatever one participant says needs to be mixed into an RTP audio stream and then spit back out to all the other users in the conference. So that's for an audio conference. Our conferencing server can also provide advanced functionality like video conferencing, and if it can provide video conferencing, it's just one step away from doing a screen sharing conference. So this conferencing server could do anything from voice all the way up to video and screen sharing, and the competing products are Cisco WebEx, Avaya Scopia, and Microsoft has a live meeting product that does something very similar to this. Because it's going to be taking in so many live streams and mixing them, it has huge CPU horsepower requirements. The final portion is something that's a little bit outside of unified communications and more in the realm of contact center or customer experience, and this is our contact center component. It's actually a system made up of a number of different components, and the main component here is our contact center routing in the middle. The purpose here is to say I have a support center or some group of resources who are going to be answering calls. I need to route calls to these agents or resources based on their skills, based on how they're available, based on who has been on shift and hasn't answered phone in the longest time. And I need to do that in a way that allows information for my customer to be sent to the agent. So the contact center routing handles an incoming call, figures out where that call should go, and then maybe takes some information from a customer SQL database here. So if the call comes in, maybe you enter an account number, or maybe it looks up your phone number automatically, and it says, okay, here's the customer information. I do an SQL lookup for that. Then I decide where to route the call, and I contact this agent desktop service here so that I can send that information down to the screen of the user, the screen of the agent who will be taking the incoming call. So that way I see that, hey, customer XYZ has called in. They called in for this type of problem because I saw that that's the button they pushed. And then I'm going to connect a call to them. Now, in the middle here is our call recording server. So remember, your call may be recorded for quality of service, and this is the piece that does that. So I've drawn it architecturally with the call going through the call recording server, but this can be done a number of different ways. The call could go through it, or it could go directly to the endpoint, and the endpoint could fork it, or the gateway could fork the call to both locations. There's a number of different things that you could do, but know that the call recording server is instructed to listen for this incoming stream, and then the stream is sent to it. So its job is to record anything that happens between the external customer and our internal agent. Then the final portion of this is our contact center reporting server. The reporting server watches everything that happens, the number of incoming calls, where they got routed to, how long they took to get answered, how long someone was on a call, what type of call, subject matter was the most frequently rang number, something like that, and allows administrators and managers to make decisions by giving them all that information about what's happening in their call center. Maybe they need to staff more people on a certain product line, maybe they need to train more people on a certain product line. This can give them a lot of information there. So why do we care about this from a Nutanix perspective? And the reason is that every one of these components that I've talked about, with the exception of the PSTN gateways and the end clients themselves, all those components are actually virtual machines. And they have different characteristics for running on the Nutanix system, and that's the part I want to talk about next. So looking at call control, this is the one that routes our calls for us. It's deployed via an OVA, meaning we download the OVA from Cisco or Avaya and say go. It requires a low latency processing because it's going to be routing a number of calls quickly. You know, you could get the speed of this system is usually measured in how many calls per second it can route, and if it's routing a lot of calls per second, that means we're going to need a lot of access to the processor. The database for this guy is typically loaded in memory because if you're routing an incoming call, there's no way that you're going to do something like an SQL lookup. That's just too slow, so they've developed their own custom routing databases. It's usually deployed in pairs or clusters of servers, and that routing database is shared between the servers. And there's a call routing thread inside of there, typically a single-threaded call routing process that handles everything that happens. So keep an eye out for any call control system and whether or not it has a clock speed requirement, because some of the systems, such as Cisco or Avaya, say, well, you need to have a CPU of at least this speed, so that'll determine which Nutanix platforms are viable options. The the number of vCPUs this guy might require are completely variable based on the size of the machine. Typically, you're going to scale these out by adding more servers, but you can also scale them up in certain instances. You're going to have CPU requirements and reservations. You're not going to allow any oversubscription, and the disk configuration is not really going to be variable. So it's going to come from the OVA. You're not going to be able to tweak this for performance at all. That's pretty common actually across most of these unified communications VMs. It'll use a lot of IOPS at boot and maybe for logging call records, but other than that it has pretty low IOPS utilization because everything happens in memory. Our next section is voice messaging. This is the guy terminating our voice calls and leaving messages for us. Very similar, deployed via OVA, but it's not going to be quite as CPU intensive. Really, it's going to be storage heavy for holding all of these messages. A lot lower number of CPUs. It's going to be doing some real-time transcoding of our audio streams, so it can also do sometimes like speech recognition or save it into a higher compression format. So that's going to take up some CPU time, but nowhere near as much as the call routing. The storage configuration, again, usually not configurable for how many disks they have, and how much storage IOPS used is typically dependent on the number of incoming calls at any one time that are being recorded or being played back, but it's not really a huge usage of IOPS. It's more going to be something that sits and takes up space. Instant messaging and presence is the one that provides our chat services. This guy is usually scale out as well. It's routing our chat messages, so it needs a lot of access to the CPU. But because it's routing messages, it needs low latency to do that. It keeps that routing database in memory. And storage is really only going to be used for logs and boot up. Any number of CPUs depending on how many users are connected to it, and it's going to require full vCPU reservations typically. So if it says I need 4 vCPUs, it'll probably require you to reserve all 4 of those vCPUs. And again, not a lot of IOPS and not a lot of configurable disk options. The conferencing server is again deployed via OVA, but unlike some of the other services, it's really a scale-up service rather than a scale-out service. So the reason for that is we need to bridge audio streams from multiple participants on one server or one processor, and if that happens, that means that all those audio participants need to connect to the same server for that to happen. So it's going to require a lot of CPU to mix all those streams together. And that's why this might be one of the largest footprint devices that you could deploy as one of these conferencing, such as Cisco WebEx or Avaya Scopia. And really, when we look at deploying these in a virtual environment, this product has the strictest co-residency rules. So it may something like, take this host with 20 CPUs or 40 CPUs and dedicate entirely for these 2 virtual machines or this 1 virtual machine. So if you're looking at deploying conferencing, you might be dedicating an entire node just to the conferencing system. And that's going to be something where you need something that's not quite storage size heavy, but really just has a lot of eCPUs. Variable amounts of CPUs and RAM here, and usually multiple disks. And it's going to be the one that has probably the most IOPS, because if you're taking all these conferences in, the thing that is like a table stakes feature for conferencing is recording. So recording all these incoming streams can be quite storage intensive. Our contact center is a little bit different of a story. There are multiple application types here, so the performance of each individual application actually kind of varies a little bit. The contact center routing, that's going to look a lot like the call routing system. The call recording system, that's going to look a lot like the conferencing or their voicemail. Agent desktop services is kind of a like call routing, and the reporting system might be database intensive. So what you have to do is kind of take a look at that contact center environment, get the specifications for the types of virtual machines that are going to be deployed, because these can all be mixed and matched in any combination. And we really need to get those specifications from the implementer of the contact center environment. So typically though, it'll be a lower number of eCPUs. It again will have reservation requirements, and depending on the call activity, this could also have the machines in the communications environment that have the highest amount of IOPS. So again, remember, when we're talking about IOPS in the UC world, we're not usually going to do a lot unless we're talking about conferencing or contact center. Those are going to be the two big components that are storage intensive. So let's shift gears a little bit from the individual components and look at how we take all those individual components and put them together on a Nutanix system. So I've shown three 20-core nodes here, three 20-core Nutanix nodes, and I've taken four vCPUs, and I've reserved those just for the controller virtual machine. Then I took a look at all the applications. In this case, this is just an Avaya example. I've taken the different Avaya applications that I might use, and I've staggered them out in a way that just lets me visually see what my CPU reservations look like. So in this case, SMGR is my Avaya System Manager, CM Duplex is my Avaya Communication Manager, and I say that, okay, they reserve 3 vCPUs, so I'm just illustrating that so I can see where to put them. Note that what I've also done is I've staggered machines of different types on different nodes. So my CM Duplex runs here on the first node, my second backup copy of CM Duplex runs here. When we're sizing out these applications, let's say for CM and Session Manager and Presence, anything that runs on 2 nodes has probably been designed in such a way that, let's say that this CM's maximum is 10,000 users. So I can maybe support 10,000 users with this one CM or this one Session Manager. Well, what we've actually done is we've said, take 5,000 users and put them on the first one, take 5,000 users, put them on the second one, and this CM has been sized for 10,000 such that if one individual node fails, this application could support the entire workload. So redundancy is built in at the application level and sized accordingly. So to get to this point and to do that layout, we actually had to get some information from the design team. So it's not going to be Nutanix who's coming in and dictating how many Aura session managers you need and of what size. It's going to be the customer's unified communications design team. They're going to say, all right, we need this many communication managers, this many presence servers, and they need to come to you with the information about the number of vCPUs for each virtual machine, how much RAM that's going to need, and how much storage space that's going to need. You're also going to need to look at the reference architectures that we've put together, because different vendors don't really have as much of a handle on what storage their own applications require. And so to piece all those pieces together for things like what the IOPS are and what the CPU reservations look like, the reference architectures that I've put together for Nutanix kind of hold all that information. And I've pieced it together from various components out on the internet, from the official vendor documentation that's spread all over, and just from my own experiences. So you can get an idea of what the system's actually going to perform like by taking a look at what the requirements are from the vendor, and then at our reference architecture for that individual product to get a whole picture of what it's actually going to do on the Nutanix system. So this is a table that's taken from the previous example. So you can see the requirements, and this image I laid out previously was just the vCPU portion of those requirements, but we also want to take a look at the RAM and storage requirements. And what we find actually is that for this system, the RAM and storage requirements are negligible for what the Nutanix servers actually provide. And that's why I've decided to focus on the vCPU and illustrate that, because that's the component that's where we're the most constrained on space. Now, if you got into a situation where a component was really looking at stressing the storage requirements or the IOPS requirements, you might want to evaluate whether or not you do some modification to these diagrams to actually denote how much storage each individual piece might use. So that's all I have to cover for unified communications. I'd be happy to answer any questions. You can take a look at all these documents that I've posted here. So we have best practices for Cisco unified communications. We've also discussed Microsoft Lync best practices, the IP Office reference architecture, and there will be in the next couple days here published an Avaya Aura reference architecture. So you can contact me for any questions you have about these. And we also have set up the Nutanix Next online community with a unified communication section underneath different applications and workloads. And we'll have a section to discuss each one of these different applications in more detail on the Nutanix Next community at next.nutanix.com. Thank you for your time.